So, design patterns then. Now, design pattern, we've talked about it a bit in class, is a general design principle. It's an encoded experience. It's a solution that people have tried and know it works, and they've documented it so that others can learn from their experiences. Um, it's a structured format, so we know when we read a design pattern, we know what to look for. We know that there will be a problem description. We know that there will be a description of a solution, and there will be usually an example and a few other things like consequences of using this particular design pattern. They have a name, and this is important because this means that when we talk about our design, we can talk about groups of classes that belong together in a design pattern. So when I'm saying that in this part of the system I am using a strategy pattern, this means a certain thing, and we can interpret what we see as members of a strategy pattern. And then you know something about the responsibilities that these in these classes that are involved in the strategy pattern, what they should do. There are different levels of patterns. We can go from all the way from architectures, where you have systems, you have subsystems, you have components, you have modules, you have computers and memory spaces and all sorts of things on that very high level. And then you have design levels, which are where you would normally see design patterns, where you have classes and groups of classes and how they interact with each other to solve a particular problem. Lower than that, you have idioms, which is one class and functions within one class. There are a few idioms in the Gang of Four book, but it's not something that's used very often. And then we have the GRASP patterns that are presented in the Craig Lahman book. They are in some sense orthogonal to the other design patterns because they are more about sound object-oriented principles. So when you use a GRASP pattern, you're basically using object orientation, and many of the design patterns that you find in the Gang of Four book are implicitly assume that you are using the GRASP patterns or some other form of them. GRASP patterns, they're nothing new, they are a repackaging of other principles with other names, and he's just put them into the context of this book. They are supposed to be a learning aid for doing object-oriented design, and their main job is to give advice for how to assign responsibilities between different classes. So these are the GRASP patterns. They are divided into two chapters in the course book. If you look at the inside of the book cover, you'll find listed and brief description of them. And then if you go into the different chapters, you'll see more discussions about how they work and how they interact and the consequences of using them and so on. So for the rest of this presentation, I'm going to go through them one by one. This is going to be boring, and but that's the nature of reading or talking about patterns one by one, is that it's like reading a phone book, essentially. Information expert, that's the first one. And the problem we have is that we need some sort of general principle for how should we assign responsibility. Assigning responsibility for doing things in particular and for knowing things. So who gets to do a certain thing, which of the classes, and who gets to know and be aware of certain information. And the solution is to have to identify information experts. So if I'm looking for some class who can have the responsibility for doing a particular thing, well, that class who also has the information to work with it should be the class doing it. That's the information expert. So in the example here, we have sale line item, and we have a product description. And some one of these classes, some one of these three classes should, for example, be responsible for knowing the grand total of a sale, knowing and calculating that for that matter. And who's got the necessary information of this? Does product line description have the right information for knowing the grand total? No, it doesn't, because it doesn't know how many sales line items we have or what other sales line items we've bought. The sales line item can't be aware of the grand total because it's only aware of itself. It doesn't know what other sale line items there are. So the sale should be aware of the grand total. That's the information expert. The sale has the ability to calculate the grand total by looking at all the sales line items. On the other hand, if I'm looking at what's the price for one particular sales line item, so I bought 5 cans of Coke, I get the price, and who should calculate the price for 5 cans of Coke? I can't put it in the product description because the sales line item contains the quantity, so the product description doesn't know the quantity. I could give it to the product description and let that calculate, but that's a bad idea. The sale shouldn't have to know the price of each individual can of Coke. All it needs to know is that this particular sales line item costs, well, the equivalent of 5 cans of Coke then. So this leaves us with the sales line item. This is the information expert. It's got the quantity, and it has to know how to get the price for 1 can of Coke, and therefore sales line item, according to information expert, should be responsible for calculating the cost of one sales line item as well. Okay. Next pattern, creator. So, who is responsible for creating a new instance of some class? Same idea here, basically, who gets to do things. And there are some rules here. We can assign class B the responsibility to create an instance of class A if B contains or compositively aggregates A. So if B is completely responsible for A, yeah, then B should create A. B keeps records of A or uses A very closely. Or for that matter, if we use an information expert pattern here, if B has the data to initialize A, then B should be responsible for creating A. So in the example, same example, who gets to create instances of sale line item? In this case, it's fairly obvious because there's only one class that is, let's say, above sale line item, that's sales. So sales should create sale line items. If we had thrown in a few others, if we've had thrown in the point of sale system as one class, that one might have been responsible for creating the sale line item, but since we've got this contain relationship, we can just as well make sure that the sale is responsible for creating sale line items. It's also a matter of that the sale records sale line items and uses them closely. So there's a lot of these principles that hold true between sale and sale line item. So therefore, sale should be the creator of sale line items. It is not as clear in this example that sale line item should be responsible for creating a product description. Probably not. Product description should probably be created by something else, and sale line item should just get the right product description. Low coupling is one of those principles that we strive after when we do an object-oriented design. We want to, on one side, we want to have the right object connected to each other. On the other hand, we don't want unrelated objects to be connected to each other. We want to have as few connections as possible. Otherwise, you get one giant ball of mud where everything is connected to everything else, and this makes it very hard to maintain, very hard to understand the code, very hard to understand if you modify in one place, what other places will be affected by that change. You will have ripple effects if you have too many connections. So you want to have low coupling, you want to have low dependency, low impact of changes, and thereby you get an increased potential for reuse. And the solution is to make sure that you assign responsibilities in such a way that you get lower coupling. So I've got an example on the following slides. Let's assume we have three classes: payment, register, and sale. Register is probably the cash box deposit at the checkout counter. So let's use the creator pattern first, because we've just introduced it. We have someone, the cashier, says make payment. And so we create a payment. And then, because I've got the register's got the information to create the payment, the register has information about how much is due and all sorts of things. So, sure, let's register, create the payment, and then I add it to the sale. Now, what this means is that the register needs to be aware of both payment and sale in order to deal with the make payment. So if we use low coupling instead, we say that the register is only aware of the sale and passes on the message, hey, it's time to make a payment. And the sale, who is also going to be responsible for this payment object later on, creates it. So in a sense, you could argue, yes, that this is another case of the creator pattern, that sale is the one who's going to be using the payment, sale is the one who's going to be containing the payment. But we could argue in the same way for having the register create the payment. Controller, next pattern. So we have the user interface layers, and they get all the interaction that the user does against the system. But after that, what happens? So what first objects should be responsible for taking care of a system operation and coordinate that it's actually being done? We don't want to do this inside the user interface code, because the user interface code is usually very dirty and full of things that has to do with the user interface, creating buttons, linking them to each other, making sure that they're laid out properly and everything. So we don't want to have business logic involved in there. We want to separate that. So what we will do is that we'll separate this. We'll have the user interface and we'll do all the things here. We've got a JFrame, so this is probably a Java system then. And as a result of what happens in the user interface, we then call what we would say, this is the main entry point to the system. We've even named it system. And we've got the enter item method call that we had before. This overall system thingy is a facade. It's a facade for the entire system. So everything that goes into this system goes via this one. This can, in a small system, work, but if the system gets bigger, it's going to get bloated. You'll have all the method calls that anyone can ever do into the system in one big class, and then that one has to delegate it further. Another option is that we make one of these classes for every use case, or for groups of use cases for that matter. So we can have, let's see, what did I mean here? Yeah, just different typical names that you'll find of these. You can have, let's say we have the use case name make payment. So we'll have make payment handler, make payment coordinator, or make payment session, if that's a relevant thing. So that's just examples of how we may name them. This enables us to have a smaller set of functions or methods into the system in each of these use case managers or use case coordinators. Then they are then in turn responsible for coordinating that what should happen when I call this enter item method, for example. Well, this controller is responsible for creating the right objects underneath or inside the system, assigning different objects to each other, associating them, setting attributes, making sure that the objects do what they're supposed to do in order to fulfill this enter item request. So they control the system operation. Sort of like a conductor in an orchestra. There is I haven't got it here, but sometimes you also see that you have one controller per role in the system. So if you're one particular type of user, you may have one controller. So cashier can be one controller, customer can be one controller, anonymous customer might be another controller. I've seen that in some cases, but same idea. It's just a different principle for deciding who gets to control a system operation. High cohesion. So we want to have our objects focused so that they only do a small set of tasks. They should be understandable. Because they're only doing a small set of tasks, they are easy to understand. You can focus on one problem at a time. This makes them more manageable, because you know that you don't have to worry about other behaviors. There's one behavior, one set of functionality, one problem that is solved by each class. As a side effect, support low coupling. Well, I disagree there in some sense, because you want to have low coupling, but if you focus on high cohesion, you will have higher coupling. So they are in conflict with each other in some sense. But the problem then is that how can we get high cohesion and also to some degree support low coupling? The solution, and I've copied this straight from the book, is assign a responsibility so that cohesion remains high. That this doesn't say anything at all compared to what the problem was, but all right. But what we should do is that we should avoid God classes that do everything in the system, controllers that are bloated, controllers that take care of more use cases and more responsibilities. And the solution to avoid these things is to refactor. We break things up into smaller classes. We define more narrow responsibilities. There's a subpattern of high cohesion, which is called Don't Talk to Strangers. This is not found in the book, but I've got a few slides about them anyway. So let's see. We have a system. We have the point of sale system. We've got sales inside this, and we've got payments. The sale is responsible for payment, according to creator and information expert, as before. And when it's time to calculate the amount due, we want to see the payment information. So we get the call get amount, we get the payment from the sale, and then we get the amount from the payment object. This is a bad suggestion, because the point of sale system doesn't know about payment. The payment, therefore, doesn't know about the point of sale system. So they are strangers. This means that the system's cohesion as a whole is lower, because you have unrelated objects talking to each other. What we can do instead is that we make sure that the sale object has a get amount method as well. So we get amount from the point of sale system. This one calls the sale to get the amount, and the sale is responsible for taking care of its payment information and gets the amount from the payment. This is a higher cohesion because it's only the sale who has to know about the payment. So this actually has lower coupling as well. It also means we've got an information expert. Sale is responsible for taking care of the payment, and if you want to know anything about the sale items, the number of items, the type of items, whatever you have, which customer was involved, the payment made for this particular sale, well, it's the sale class and objects of the sale class who are responsible for keeping track of this. If you want to have any of that information, you go to the sale object, and that will pass on to you the information. What happens here, this is a bit ugly, because you have a private variable or private attribute of the type payment, and you happily just give that away. I ask you, get payment. All right, here it is. Here's my private data. Do what you like with it. I have no clue at all what you're going to do. You may update it, you may delete parts of it, and you may corrupt the data to any degree. I don't care. Here it is. That's a bad idea. With this solution, you are still in control over your private variables. You give the information that is requested, and only that information, and you do not enable anyone from the outside to mess with your personal and private variables. Okay, polymorphism, next pattern. If we want to handle different alternatives based on the type of an object, so that we can create pluggable software components, we can extend them, we can add more different versions later on. Well, we could do this with a giant switch case statement, but it's better to use the methods we have available in the programming language itself. In this case, if we're using an object-oriented language, we have polymorphism. This is something that we're using in almost every bigger design pattern in the Gang of Four book. And the idea is that we have an abstract declaration of a class and a few methods here, and then we implement this particular method in specific subclasses, in concrete subclasses. If we want to add a different payment, Apple Pay, well, we add a new class here, and we implement handle payment according to how Apple Pay wants it. This makes it extensible. We can easily add new payment methods, and we don't have to go in and modify any of the existing code, here at least. We need to modify the one that decides that it's an Apple Pay that we're doing, but that's just one place rather than several places. So this is one instance where polymorphism helps us to deal with this. And also we don't have to check, are we dealing with a check payment, credit payment, or cash payment? We just use a payment object and let the compiler take care of which of the subclasses it actually is and calls the right method. Pure fabrication. So you will end up in situations when there is no clear case, no clear class that should take care of a particular responsibility. And the solution then is to invent a class. So if I'm doing the payment thingy, I may want to store this so that I can do my bookkeeping later on or whatever. And I could put that into the payment class, but that means that the payment class is responsible for both managing the payment and managing persistent storage. And I may want to have different types of persistent storage later on, which means that I'm going to bloat the payment class with a lot of information that has to do with storage and nothing to do with the actual payment. So we invent a class. We call it persistent storage. We have the method log transaction, so the payment will call the log transaction, but let the persistent storage class take care of how this is actually stored and make sure that it's we're able to store it in different ways, and we keep it updated, we keep it consistent, and all sorts of things. Indirection. Well, there are cases where we're using we're doing things in a particular way all over the system. So in this case, for example, if we're looking at the tax authorities, these tax authorities may need to connect to them with the help of network communication. Which means that for every time we need to talk to the tax authorities, we need to open a socket connection, wait for it to be opened, and then we need to set up a package with a message with all the information about what we're looking for or what we're sending to the tax authorities, and then we need to send this over the socket. We need to get an acknowledgement signal, and then we need to close the socket. This is the extreme example where we actually have to work with network communication, which means that we need to marshal our method calls and everything. There are similar cases inside of an application where the use of one particular class, the use of a particular subsystem requires that you follow a particular protocol in terms of that you first call this method, then you do this, and then you compile the data in a particular way, and then you call another method, and then eventually you close the connection. Already in the example up here, we had this with persistent storage. So let's say we have file storage. Well, you need to open the file, you need to write to the file, and you need to close the file. And in order to write to the file, you need to have formatted your data properly. So if we're doing this all over the system, this is going to create a lot of dependencies. There will be a lot of direct couplings to these, in this case, the tax authorities, or to the file system. And if we want to later on change this, we are going to have to find all those places and change it in all those places. So to avoid this, to make it easy for us to deal with this connection in a better way, we create an intermediate object, the tax master adapter in this case, so that all calls that has to go to the tax authorities go via this one. This means that we can assign this class the responsibility for taking care of the protocol in terms of opening the socket, packaging the message, getting a return message, and interpreting the return message, and then closing the socket. This is now the responsibility of the tax master adapter here, which means that we free up this from all the other places, and all they have to worry about is that there is a tax master adapter. So there is no longer a direct coupling between all the sale, the payment, the purchase, whatever we have, and the tax authorities. This is now handled with this one. Same way in this example. Payment and wherever else I want persistent storage. Rather than having them taking care of the persistent storage, I create this intermediate object who is in turn responsible for dealing with the persistent storage, whether it be a database or a file or a message to another server somewhere or whatever. So we are introducing a level of indirection. This class is an indirection, so that rather than a message going straight to the storage, we are going indirectly through this one, which means that there's no direct coupling no longer between our main system that takes care of solving the domain problem, and whatever else system we have. Protected variations. So variability is an important thing in large software systems. And there are many different ways of dealing with it. This is just one way. But we have, so the idea is that you have, depending on circumstances, you may have different pieces of code that should be executed. If I'm in Sweden, I will have a particular protocol for talking to the Swedish tax authorities. If I'm in another country, I may have other protocols for talking to their tax authorities, for example. I may have different databases I'm talking to with a different language for them. And the idea is that here is also a special case of indirection. So first of all, I need to identify where can this system vary. And then I make sure that I get a stable interface around them. I put wrapper classes around them, which means I introduce an indirect class that I'm using in the rest of the system. And then this wrapper class is responsible for talking to the code that may vary. Many bigger design patterns, wrapper, just like I just mentioned, abstract factory, adapter, bridge, facade, and a whole bunch of other design patterns are in effect trying to do this, trying to protect the rest of the system from these local variations. So in summary, what we do is that, this is the class diagram that I started out with in the first design pattern, the first GRASP pattern. We had sale line item, and product description. And as we went on, we had the cashier or the register coming in. We add methods to this class diagram. So we started out with something that was more like a conceptual diagram, and we started adding things based on what we learned with applying our design patterns. So get total, for example, came from applying information expert. Make line item came from creator. Make payment came from low coupling. Get subtotal came from information expert in the sale line item here. The payment and the abstract payment and the subclasses here came from polymorphism. We had the let's see, which design pattern was it? It was the fabrication thing, and indirection for that matter, that created this persistent storage class here. So we add classes based on that we want to have clean responsibilities. Payment is now handling only payments, and storage is handled by a different class. We created this, which means that we are now moving more into the realm of actually building the system. This is something that is needed to for our software to be built. It's not necessarily in the problem domain. The fact that we have an abstract method here, which is concretely implemented in different ways, is a solution that we do to get help from our compiler to solve this problem, which actually to some extent exists in the problem domain. But we are now making the classes and designing class diagrams to deal with those problems that we had. So what started out as a conceptual model is now, well, looks more like a class diagram.